All right, let's dive in. Today we're tackling Benford's law. And I know what you're thinking, another math thing, but stick with us. This one's got some seriously cool real-world stuff tied to it.
Absolutely. We've got a whole stack of research here. And the more you dig into Benford's law, the weirder it gets.
Right. Like, at first glance, it's just about the first digit of numbers. Not the whole value, but whether it starts with a 1, a 5, a 9, whatever.
Yeah, and you'd figure those starting digits, they'd show up pretty evenly across, any big data set, right?
Makes sense. Total random chance.
But Benford's law is like, nope, not how it works.
So what does this law actually say? Hit me with the basics.
Basically, it predicts that lower digits, like 1 or 2, are way more likely to be that leading digit than, say, 8 or 9.
Hold on. So if I'm looking at, I don't know, a list of countries and their populations,
You're more likely to see a population starting with 1, like 1 million, 10 million, and so on.
than one starting with 9. That's bizarrely specific.
It is, and it gets wilder.
Because it's not just populations, right?
Mm.
We've got articles here saying this applies to, everything.
Pretty much. Electricity bills, the lengths of rivers, stock prices, even those fundamental constants in physics.
Okay, now my brain's officially glitching.
But that's what makes it so cool. And we're going to get into why it works this way, but think about the implications.
Oh, yeah, like that whole fraud detection thing.
Exactly.
Yeah.
If someone's cooking the books, their fake numbers probably won't follow Benford's law.
So it's like a mathematical lie detector. Sign me up for that class.
And then there's potential for analyzing election results, spotting scientific misconduct.
Whoa, 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 slow down. One mind-blowing concept at a time, please.
Fair enough.
Okay, let's back up to how this magic distribution actually works. I'm a visual learner, so someone could give me a picture to put this in.
All right, imagine a number line, 1 to 10, all evenly spaced out. That's how we usually think about numbers, right?
Yeah, totally.
But Benford's law, it's all about the logarithmic scale.
Uh-oh, math words incoming.
Don't worry, it's simple. On an algorithmic scale, the space between 1 and 2 is huge GE. But as you go up, like between 9 and 10, that space gets teeny tiny.
Okay, so it's not like the numbers themselves are biased, but how we're representing their size matters.
Bingo. You're more likely to land on a number in that big 1 to 2 range on the logarithmic scale, just by chance.
So this Benford thing, it's not about individual numbers being weird. It's about how their magnitudes distribute.
Exactly. And this is more likely to happen when the data covers a really wide range of values.
Like, I'm guessing my shoe size over the years wouldn't follow Benford's law.
Probably not. You need things like populations, stock prices, things that can be tiny or massive.
Right, multiple orders of magnitude.
And here's another kicker. It doesn't matter what units you're using.
Wait, so if I measure a river in miles or kilometers, Benford still holds up?
Yep, it's scale invariant.
Whoa, so it's like this underlying pattern in how quantities exist, regardless of how we humans measure them.
It makes you wonder, doesn't it?
Is this a clue to some deeper mathematical truth about the universe itself?
Maybe. But before we go full philosophy, let's bring it back down to earth.
Good idea. My head's already spinning.
Let's talk about those practical applications, starting with catching those sneaky fraudsters.
Oh yeah, that's where things get really interesting.
Imagine someone trying to fudge their financial records. They might be clever with the individual numbers.
But they probably aren't thinking about this Benford distribution thing.
Right. So if their data suddenly doesn't fit the pattern, red flag.
It's like trying to fake a masterpiece. The forger might get the details right.
But the overall composition, the style, it'll be off.
And Benford's law is like that art expert, spotting the inconsistencies.
Precisely. Of course, it's not foolproof. There can be legitimate reasons for deviations, too.
Right, we can't just accuse everyone whose numbers are slightly off.
Exactly. It's a tool for further investigation, not a final verdict.
A clue to dig deeper.
And importantly, just because something doesn't fit Benford's law doesn't automatically mean it's fake.
Good point. Because not everything in the world is going to follow this pattern, right?
Like telephone numbers, those are mostly assigned sequentially. They'd be all over the place with their first digit.
Or people's heights were all within a pretty narrow range.
Exactly. So it's about knowing when Benford's law is the right tool for the job.
Okay, so it's powerful, but we got to be careful not to over-apply it.
Absolutely.
I'm starting to get the hang of this, but there's still this nagging question. If this Benford thing pops up everywhere, from stock prices to the lengths of rivers, what does it mean?
The million-dollar question. And that's what we'll be diving into next time.
Back again for more Benford's Law fun.
Last time, my brain nearly melted trying to wrap my head around this whole first digit thing.
Well, buckle up, because we're about to go even deeper down the rabbit hole.
Deeper. I thought we covered, everything already. from accounting fraud to the universe itself.
We just scratched the surface. Benford's law is like this Swiss Army knife of math.
Okay, I'm intrigued. Hit me with those other uses.
Let's start with science itself. Wait, science on science? Like, scientists using Benford to check each other's work.
Exactly. It's like peer review on steroids.
So if someone's fudging data in their research, Benford's law can sniff it out.
Yep, because those made-up numbers probably won't follow the natural pattern.
Whoa, it's like a built-in lie detector for scientific papers.
Pretty much. And speaking of sniffing out shady stuff, Benford's law has also been used in financial markets.
Oh yeah, I think I read something about that, like spotting stock manipulation.
Exactly. It's not foolproof, but if stock prices suddenly deviate from Benford's pattern...
That's a sign someone might be messing with the system.
Right, and it's been used to investigate things like the 2010 flash crash, looking for unusual trading activity.
Makes sense if someone's trying to artificially pump up or tank a stock.
Those manipulated numbers will stick out like a sore thumb.
It's like trying to sneak a fake painting into a museum. A casual observer might be fooled.
But an expert will spot the inconsistencies.
And Benford's law is that expert. But for numbers instead of brushstrokes?
Great analogy. But again, context matters. It's not always a smoking gun.
Right. Got to be careful not to jump to conclusions just because something doesn't perfectly fit Benford.
Absolutely. It's more like a starting point for investigation.
A clue that maybe something deeper is going on.
Now, beyond catching the bad guys, Benford's law also has applications in understanding how the world works.
Okay, less fraud busting, more mind-blowing science then.
Exactly. Researchers have started using Benford's law in fields like genetics and even physics.
Whoa, hold up. Genetics. You're telling me this math thing connects to our DNA?
It can. Researchers are analyzing genome data, looking for patterns that might signal certain genetic conditions.
Like using Benford's law to decode the secrets of our genes. That's wild.
And in physics, it's being used to analyze things like physical constants, those fundamental values of the universe.
Now we're really getting deep.
Yeah.
So if those constants don't perfectly follow Benford, does that mean our understanding of physics is incomplete?
It's a possibility, which is why this whole thing is so exciting. It's like a tool for pushing the boundaries of knowledge.
Benford's law, it's not just about catching fraudsters. It's about questioning what we think we know.
Exactly. It's about using this mathematical lens to see the world in a new way.
I'm starting to see that, but before we get too philosophical, let's talk limitations again. We don't want to give people the wrong idea that this explains everything, right?
Absolutely. As powerful as Benford's law is, it's important to remember it's not a magic bullet.
And we can't just apply it willy-nilly to any data set and expect meaningful results.
For example, we talked about telephone numbers. They don't follow Benford because they're assigned in a very specific way.
Or like grades in school, teachers might be more likely to give a 90 than a 91.
Right. Human behavior can skew things.
So it's powerful, but not all powerful. It's about knowing when it's the right tool for the job.
And always considering the context of the data.
Okay, I'm getting a much better sense of the nuances here, but one big question still bugs me. If Benford's law pops up in such diverse areas, there's got to be some deeper meaning, right? Like, what's the why behind it all?
That's the million-dollar question. And that's what we'll tackle in part 3 of our deep dive into Benford's law.
Okay, final part of our Benford's law deep dive, and my brain is officially fried. We've seen how it works, where it's used, but the big question still lingers. Why? Why is this pattern so widespread? What's the cosmic reason?
It's a question that's kept mathematicians and scientists up at night for a while now. And there isn't one simple answer everyone agrees on, but there are some really compelling theories.
Hit me with those theories. Got to be better than me just staring at spreadsheets wondering how.
One of the leading explanations has to do with how a lot of stuff in the real world grows or shrinks in percentages, like stock prices, populations, even how fast rumors spread online.
Right, we touched on that. Those fluctuations, especially over time, they create a huge range of values, and that seems to naturally lead to Benford's law popping up.
Exactly. It's not just about the numbers themselves, but about the dynamic processes that generate them.
Okay, so Benford's law is like a side effect of how much stuff in the universe is constantly changing.
Pretty much. And those processes, they happen on all scales, from tiny bacteria to the entire stock market.
So it's like this underlying principle of growth and change, and Benford's law is just its shadow.
A pretty revealing shadow. But that's not the only perspective. Another interesting idea comes from the world of information theory and this thing called entropy.
Okay, I've heard of entropy, but always had trouble wrapping my head around it.
Well, in simple terms, it's a measure of how disordered or random something is. Think of a messy room, way more entropy than a perfectly organized one.
Got it. More mess, more entropy.
Now, some researchers think Benford's law might actually be a consequence of systems trying to maximize entropy.
Whoa, hold up. So Benford's law is a result of the universe loving chaos.
In a way, yeah, it's kind of counterintuitive. This seemingly ordered pattern might be a reflection of underlying randomness.
Like the universe is always trying to be as messy as possible.
And Benford's law is what happens when it plays out in the world of numbers.
My brain officially hurts, but in a good way.
That's the fun part. And these are just two of many theories. We're still figuring this whole thing out.
You know, this whole deep dive, it's like we started with a simple math trick. But the more we dug, the more we realized how deep and profound this whole thing is.
It's like that with a lot of science, right? You pull on one thread and it unravels a whole universe of questions.
Totally. Benford's law, it's a tool, a mystery, and a whole philosophy wrapped up in one.
It reminds us that the universe is full of surprises, even in something as seemingly basic as numbers.
Couldn't have said it better myself.
Huh.
And that's a wrap on our deep dive into Benford's law. We hope this sparks some curiosity. Maybe you'll spot those Benford patterns out in the wild now. Until next time, keep exploring, keep questioning, and keep those digits flowing.